Okay, all right, so welcome back. Okay, and so what we're going to do is we're going to move on to our next part, which I kind of called Intro to Quantum Optics, but that's, that may be overselling it a little bit. What we're going to do in this part is we're going to be talking about basically slowly introducing NMR and a single photon qubit system, and we're going to look at those systems. Okay, and on the way to doing those, I'm going to be bringing in concepts from quantum optics. Okay, so intro to quantum optics, but really this is NMR and a single photon qubit model. Okay. Now, so what we're going to be doing in this chapter, I'm going to basically try to introduce the important things to understand, so we'll be able to deal with other systems. So we're going to be talking about physics, okay, that will later be important to systems like trapped ions, cavity QED. That's those Rydberg atoms flying through cavities. Circuit QED. That's superconducting qubits, and so on. Neutral atoms. Quantum dots. NV centers, etc. Okay, so we want to build the basis so we can understand basically the physics of all these systems, whether we go through all of them or some subset of them. Okay, so this is the main purpose of this, and what we're going to do is focus on these two models. Okay, and what I want to start off is remind you of what our world looks like, what the real world looks like, at least the real world in our low energies earthly scale. Okay, and in our low energies earthly scale, you can just take quantum field theory, and that describes basically everything we know. Okay, and that's great. And if we simplify it even further, then at the end of the day, our world, and I showed you this in the introductory talk, our world is basically composed of atoms, which you can think of as nonlinear quantized systems. Okay, so systems where the energy level spacings are not equal, and bosonic modes. Okay, and these are just represented by harmonic oscillators. Okay, and these bosonic modes, these are electromagnetic modes, phonons, magnons. And they will, they describe cavities, lasers, microwaves, all those things. Okay, well, cavities, lasers, and microwaves are all electromagnetic modes. All these are bosonic modes, basically harmonic oscillators. Okay. And the atoms, well, your fermions, and whatever different atoms you want to take, these are basically nonlinear oscillators. Okay. And in the context of quantum technologies, we want to ask the question of, okay, so this is our real life. This is our world. It is composed of these things. And up until now, in this course, what were we talking about? We were talking about something very abstract, the Anyone? What were we talking about? We're talking about a qubit.
Qubit.
Yeah, we were talking about a qubit. Okay? And at this point, we want to just ask the simple question of what is the qubit? Okay? All right? We want to realize a qubit now. Okay? So we understand quantum information. We're very good at all those calculations. Maybe you're good at it. I don't know. But we understand all that on the abstract level. Now we want to realize a qubit. Okay? We want to realize many qubits. We want to realize a quantum system. Okay? And we already know that a qubit is simply 2 levels. So the simplest way to realize a qubit is to do what? Anyone? Ofer. What do we do to realize a qubit?
Define which 2 levels we're working with?
Yeah, take 2 levels and work with them. Okay? So the simplest way is to take 2 levels of an atom and decide, okay, this is my qubit. Okay? There are other ways to do it, though. Anyone know other ways? Yotam, who's just joined us with video. He fixed his video camera. Woohoo!
Photons with the kituv, polarization.
Photons with polarization. Where does that work in this diagram?
In the bosonic modes.
In the bosonic modes, right? And those would be continuous variables, right? With their polarization. Very good. Could also take, 0 and 1 here to be a qubit. Who says yes? Who says no? Vote. Oded is unsure, or he's not here anymore. Okay. Noam is also unsure suddenly. Okay. So in general, yeah, I can take these 0 and 1 and make them into a qubit. The main problem with this, and you will see this moving forward, is that, and we will see this on a 2-level system. If you need to be able to control your qubit. So just to define this Hilbert space as my qubit is great. But just to take this 0 and 1, this is a linear system. You cannot control your 0 and 1. Think about a classical harmonic oscillator. If you put in more drive, more energy, what happens? It just swings harder. It means that if I send in microwave light at some h bar omega, and h bar omega is this, what will happen? I will start climbing up the ladder. Okay? So to be able to utilize this 0 and 1 as a qubit in a bosonic mode, I need some way to cut off the rest of this Hilbert space. But on a theoretical level, it's possible. So if I have control, I can. But if the only thing I have is this harmonic oscillator and the only thing I can do is drive it, then no. Okay?
The problem is that you cannot take out the energy once you put it in.
Well, what happens is, as you start driving, we'll see this later. As you start driving, you do what is called a displacement. Okay, you create a coherent state, which basically you start off here and you're starting to populate more and more and more levels up here. In a simplified form, think of it. Suppose that Oded, okay, prepared the system, somehow magically prepared the system in this state. 2 photons in this electromagnetic mode, and now you come with your classical drive, which is basically a sine wave, okay? And you start driving the system. What happens is it's going to be driving up, but it's also going to be driving down. You don't have control over it. And suppose that you defined your qubit to be these 2 levels, and you think you want to do like an X operation to bring it from here to here, You're not. You're driving this, but you're also driving this. So you end up with some superposition of 1, 2, and 3. Okay? We'll see this explicitly in math, how when you drive an oscillator, you just start populating the levels further and further. Over here with an atom, that doesn't happen because I have here some h bar omega, and if I take a sine wave with omega frequency and send it in, what happens is it will drive transitions over here. This is not omega. This is different. So you're off resonant with this next transition, and if you're sufficiently off resonant, then we can ignore it, and then what happens is your driving will just take you backwards and forwards, backwards and forwards, backwards and forwards into a phenomenon called Rabi oscillations, okay, which we're going to see in just a moment. Okay, so what we're thinking of in terms of qubits is, so we understand we can pick two levels, and they can be a qubit. And then later we need to worry about whether can we control them, not control them, read them out, measure them, and so on and so on. But on the very basic level, any two levels will suffice, and that is good. Can we take more than two levels to be a qubit?
Theoretically, yes.
Who said that?
Yotam.
Yotam. Okay. Now in practice, is it a yes or a no?
No.
Why not?
It's much harder to control, but there are papers saying that you can use free-level system. If it's hard, it's easier to control somehow. You might use it, no?
Well, you gave us the example of the polarization. That's many, many levels, right? It's continuous levels. But also, you don't have to encode your qubit in physical levels. You can also do what is called a logical qubit, which is composed of many physical qubits. Okay, so think about the following construct. Okay, think of this harmonic oscillator with levels, and I can define a qubit as zero. A logical zero for a qubit, okay, would be 1 over normalization factor. Let's say 0 plus 2 plus 4. For example. And now, as a logical 1, all I need is some orthogonal state, right? All I need is for 0 and 1 to be orthogonal, so take some other normalization factor here, and this could be, for example, 1, maybe plus 3. Okay? So now these two states are my qubit. Okay, so your psi qubit would be some alpha 0 logical plus beta 1 logical. Okay. But now you're asking, why do you want to do that, right? Is this clever or is this stupid? Anyone have an opinion?
Everything depends on how you can.
Sorry, there's some interference between Yotam and Daniel. Do you want to speak, Daniel?
No, sorry.
No? Okay, then you speak, Yotam. One of you was trying to speak.
Everything depends on which is easier physically to control.
It depends on your control, but it has an additional importance, and it's the fact that you're now using a larger Hilbert space. And this larger Hilbert space can help you in cases of noise, something called error correction. Okay? So in realistic systems, your qubits are not great, they're not perfect, they're noisy, you might have heard of that. And to be able to deal with noise, we're not going to do that in this course, we're not going to discuss this in this course, but I do want to give you these notions and for you to understand. It is important to be able to do these logical encodings so you can error correct. Okay, the simplest example, for example, is if you take instead, suppose that you have many atoms. Okay, now you want to encode over many atoms, and let's suppose that each atom has 2 levels. So each atom is an actual physical qubit. Okay? But that qubit has some error rate. It can flip from 0 to 1. I can take now 3 qubits, and my logical 0 will just be the state 0, 0, 0. And my logical 1 will be the state 1, 1, 1. Okay? Now, if this was a classical problem, suppose that, you know, one of the bits flipped from 0 to 1. I can just ask each of the bits, what state are you? And we do a majority count, right? And as opposed to the United States, majority does count here. Okay? There are no electoral college or anything like that. I don't hear a roaring laughter. There should be a roaring laughter here. You know, I'm trying here. I need a button with a roaring laughter on Zoom. Okay. All right, we'll add that. Zoom 5.0, roaring laughter button. It's important for stand-up comedians. All right. I see I can get a smile from Nadav. Noah has a slight smile. I can see Amot is like, he's like, what? What does he want from me? Leave me alone. All right. Aviad has an emoji because his camera is broken, or his roommate stuck like a black sticker on his camera or something like that. Okay, anyway. So you do a majority count, and then you know that one of the bits is flipped. You figure out which it is, and you bring it back. So that's classical error correction. In the quantum case, you can also do similar things like that. Of course, you can't measure because then you collapse your qubit, but you can always ask each 2 qubits, you know, are you the same? Okay, and suppose that the qubits are like this or like this. You ask these two, are you the same? And you ask these two, are you the same? If both tell you no, you know the middle qubit flipped. If these two tell you yes, and that one, and if this tells you yes, this tells you no, you know this is flipped. Okay? So you can do a bit flip correction. If the phase flips, this is not sufficient. You need 5 qubits to do that. But this is a very simple example of what error correction is. And in order to do error correction, you have to be able to redundantly encode. Okay? And this is why when we talk about qubits, there are 2 notions. There is something called the physical qubit, and this is 2 physical levels that you will use. And there's something called the logical qubit, which is composed of many, many, many levels. And a logical qubit can be composed of many other logical qubits. And you can concatenate this further and further and further to make your error correction more robust. Okay? So this was like a short introduction into physical qubits, logical qubits, and what we're looking for. Okay? But for now, what we're going to do, we're going to take all the way a step back. And we're going to be talking about a 2-level system. Okay? So we're going to be talking now about the simplest physical qubit. Okay? The simplest physical qubit. And the simplest physical qubit right now is a 2-level system. And even before we talk about the simplest physical system, a single qubit, we're going to talk about a classical spin. Okay? A classical magnetic moment. Okay? So we're going to start with a classical magnetic moment. And a lot of what I'll be doing, I'll be following the book by Charles Slichter, okay? His NMR book. And what we're going to be doing here with this classical magnetic moment, okay, we're going to do the dynamics, and then I'm going to show you that a quantum version of this has the same dynamics. Okay, so we're going to go from classical. I'm going to show you phenomena of a classical magnetic moment. We're going to see how they arise. Then we're going to see the quantum version. We're going to see that that's the same. Okay, so we will get intuition from a simple classical example that you might have seen before and is easy to do. And specifically, what I want to do is I want to show you on this classical system two typical quantum phenomena. So two things which are typically referred to as quantum. The first one, Rabi oscillations. And the second, something called rapid adiabatic passage. Where in the quantum version, some of you may know this as Landau Zener transitions. Okay, so we're going to see how these two arise in their classical version. Okay, so let's start very simply with a magnetic moment. And the Hamiltonian for a magnetic moment, the interaction Hamiltonian with the magnetic field. So classical magnetic moment, classical field, nothing quantum here for now, minus mu dot B. Okay. The torque is given by mu cross B. Okay. And if you think of a compass needle or some current loop, you have some current loop with an area A and a current I going through it, then mu is just going to be A, I in the Z direction. Okay? So A times I in the Z direction. So this would be like your magnetic moment. And then the angular momentum of this magnetic moment, or the time derivative of the angular momentum of this magnetic moment, is the torque, which is written up here. So that's mu cross B. And mu itself, we can just write basically as the gyromagnetic ratio times the angular momentum. Okay, so mu, maybe I'll write it here. Mu is gamma L. Okay. So now we can write the equation of motion, which I'm sure you've seen in one of the classes. So L dot equals gamma L cross B. So this is our equation of motion. And the solution to this equation of motion is, anyone that remembers this?
Alarm oscillations.
Alarm or oscillations, exactly. We get a precession. Okay. So the solution, I'll write here the solution, we get a precession at omega L, which equals gamma B, or minus gamma B, the way I've defined it here. Okay, so this is the solution. And just to give you some numbers, for electron spins, so gamma E, for electron spins, this comes out to be 2.8 megahertz per Gauss, and for protons, this is 1.4 kilohertz per Gauss. So if you put 1 Tesla, you will get 28 gigahertz Larmor precession for electrons, and for protons you will get 14 megahertz precession, so about 1,000 times slower. Okay. Now these are quantum things, the electron spin and the nuclear spin, but this is just to give you numbers, so you get the orders of magnitude. But the Larmor precession is just, it's a classical magnetic moment that precesses. Okay, so we only have 2 minutes, so maybe I'll I won't continue with this right now in the 2 minutes that I have. So what we're going to do next time, though, is we're going to take this equations of motion and we're going to go into the rotating frame. Okay, and in the rotating frame, in the frame that's rotating at the Larmor frequency, what would this magnetic moment look like? Anyone?
Constant.
Constant. Okay, it will be just static. Okay? And then what we're going to do is what people do in NMR. We're going to add an AC field, and we're going to see that in this rotating frame, this AC field in the lab frame will cause the spin to rotate. The magnetic moment to rotate. Okay? And these rotations are the classical equivalent of Rabi oscillations. Okay, so that's what we're going to do next lesson. Start off the next lesson with that. And then I'm going to show you what happens when we sweep the magnetic field through, okay, or sweep the frequency of the drive through and get something which is called rapid adiabatic passage. Okay? And then I'm going to show you how it comes about in quantum dynamics, or in the quantum version. Well, basically, they're equivalent. Okay? And that will conclude our discussion about a magnetic moment and a magnetic spin. Okay? And then from there, we'll be able to progress into what NMR looks like, and we'll be able to describe what an NMR quantum computer looks like. Okay? So from here, we're going to be going forward, and then in about next lesson maybe, or the lesson after that, we're going to build an NMR quantum computer. So and so. Okay? All right. Do we have any questions? Anyone? Everybody's happy? Okay, good. All right. So, thank you. And if anyone wants questions, they can stay on the Zoom and ask me questions, off camera or whatever.